Good morning. Today I will discuss about gas dehydration. Gas, natural gas, whatever you are getting from well bores are separated from oil, condensate. Finally, you got natural gas, but still it will be containing certain amount of water. So water may be in terms of vapor or small water droplets. So you have to remove that water droplets, otherwise there will be some other issues. For example, it will be forming gas hydrate, or it will be forming ice, or it will be creating corrosion. So it will be blocking path, corrosion. So this sort of issue, again, it is not having any heating value. So if it is sending to your customer is burning in your, let's say, Indian gas cylinder, you are getting water content also, some small amount. So that water will be evaporating. It will not. It will take lots of heat. It will take because of phase change from liquid to gas, but that heat you cannot recover or you cannot use actually. So that will be wastage of heat. So just to avoid all this wastage of heat, which avoid corrosion, avoid forming gas hydrates, avoid forming ice or plugging your flow path, you have to remove the water content, otherwise sells your customer, the customer in downstream, they will not buy your gas. If you are selling also, there will be issue like gas hydrate formation, ice formation, corrosion, and uh, low heating value of your fuel. So how to okay. So then how to isolate water from gas? Okay. So there will be again similar sort of column. Okay, absorber column. Okay, or glycol contactor they say. There will be several other method also. Just one simplest method, glycol contactor column will be there. You put water plus gas, or gas having some water content. So you get dry gas and lean glycol solution. You inject from here, you take rich or it is having lots of water content, glycol solution. Okay, and again you reprocess or reproduce glycol, again re-inject. So this cycle will go on. Okay, and in between there will be reboiler system, there will be pumping system, there will be valve mechanism. So several items are there. The simplest way is that to explain absorbing water. So this is glycol contactor column, then the whatever water with glycol, that solution you got, that is called rich glycol. Rich glycol will go to reboiler section or regenerator section. Okay, so reboiler regenerator section, you are producing lean glycol solution. So the lean glycol will come to your absorber section, you are getting dry gas, and your water will be disposed, whatever water you are getting. So whenever you are dehydrating gas using glycol, so there will be some simple method. For example, you can have absorption mechanism, you have adsorption mechanism, you have condensation mechanism, you can use chemical inhibitor. So absorption means like you have diethylene glycol or some other type of glycol you use. So the glycol will be absorbing water particles, and it will be you will get gas without water, or water vapor or water liquid. Then there will be some adsorption process, or solid desiccants are there. So if we pass natural gas with water, so water will be absorbed in the solid and you will get water free gas. So similarly, condensation, you reduce temperature, at very low temperature water particle will condense, it will form liquid, it will be deposited on the bottom, and you get gas water free. You can use chemical inhibitor also. Okay, so if you use chemical inhibitor, so that gas hydrate formation will not be there, so that mechanism also there. Okay, and condensation, you can use external cooling system or refrigeration system or cryogenic system you can use, and you can reduce temperature very low, you condense it, or you can make small ice particle and separate. Okay, turbo expander also you can use to reduce temperature, and you can separate water particle there. So absorption unit using liquid desiccant like glycol, methanol. Absorption section, adsorption using solid desiccant like alumina or silica gel you can use for adsorption. Cooling and condensation, if you see below the dew point, you reduce temperature, so fluid water particle will be creating droplets, small droplet, then you separate. Okay, you can expand also or you can refrigerate also. Why dehydration? So hydrates are solid formed by physical combination of water and hydrocarbons. IC compounds of about 10% hydrocarbon and 90% water grow as crystal plugs the lines of flow path, it will be plugging. Primary condition of hydration, less temperature, uh, dew point less than dew point temperature, okay, with free water present, low temperature and high pressure. Okay, so pressure high, temperature low, in that case also hydration formation will be there. Corrosion, water plus acetic gas promote corrosion. So if water is there, then metal part can be corroded or reaction will be happening in iron. Downstream processing, presence of water may cause side reaction forming, foaming or catalyst deactivation. So for all these reasons you have to remove water. Inhibit hydrate formation, hydrate formation, like hydrate forms at high pressure and low temperature, and liquid must be there, liquid water. Okay. So how to prevent? Raising the system temperature or lowering pressure. So you reduce pressure, increase temperature, hydrate will be vanished. So downhole regulator, so chokes, pressure regulator installed at downstream, so their pressure or temperature will be changing, so the hydrate formation will be there actually. So you have to check whether heating will be required there. So indirect heaters or direct heaters can be used. Wellhead and flow lines heaters uh, can be heated, that can be heating this natural gas. It will be maintaining flowing temperature and hydrate above the hydrate formation temperature. And some cases you inject chemical to inhibit hydrate formation. So methanol or glycol to depress freezing point of liquid of water you can use, so that hydrate will not be formed. Dehydration, removing water vapor from gas liquid and water drop out, so depressing the dew point. So you depress the dew point so that gas hydrate formation will not be there. Okay, so glycol dehydration when you are doing, so you will have similar like in amine separator system. You have seen one contactor column or absorber column will be there. Here also we have similar mechanism, contactor absorber column. You have several trays. Sometimes they call bubble column also. Okay, so glycol, this is a hygroscopic method, hygroscopic, not hydro. This is hygroscopic. It is absorbing moisture. Okay, so if moisture is there, you add glycol. A glycol will be absorbing moisture and gas will be free from water. Okay, uh, water vapor gets dissolved in glycol liquid. Okay, glycol dehydration cheaper, water easily boiled off. Okay, now you got water and glycol mixture. You increase temperature, glycol and water will get separated because of boiling point difference. Water will be boiling 100 degrees centigrade, but glycol will be boiling at higher temperature. So you increase temperature to 100 degrees centigrade, water will be boil off and you will get pure glycol. So that glycol again you inject into your contactor column. Okay, contactor column. And it will go to regenerator section where you will be regenerating glycol using temperature, let's say 100 to 400 degrees Fahrenheit, centigrade temperature. At lower temperature water will be boil off. High temperature you are not creating high temperature to boil glycol, rather you need glycol liquid and water create steam and separate it. Okay. Okay, so this is taken from Wikimedia Commons. You see this one, wet gas is entering. Okay, wet gas, and this is glycol contactor column. Okay, so from there rich glycol is coming here, and it is going to be flash chamber again. If you have any hydrocarbon or anything, you are separating, and this flash chamber exit gas is going to heat exchanger. Okay, from there it is going to your reboiler section or regenerator section. Okay, and whatever pure glycol coming, it is okay, it will coming like this, and pure glycol. Okay, some error is wrong. So this is pure glycol coming and it is going through this and it is going through this, and lean glycol coming and entering here. Okay. So this is rich glycol, and this is lean glycol. Okay. So lean glycol coming from your regenerator section, heat exchanger is here. From heat exchanger it is going through this glycol pump to your contactor column. Contactor column is things are getting absorbed, water getting absorbed, rich glycol coming, flash chamber to heat exchanger to your glycol separation unit. Okay. And water at high temperature it will be vapor, so you are getting water here. Okay. This cycle will continue when you are working, you are separating water from gas. So, what are the different glycols? Ethylene glycol. Ethylene glycol is high vapor equilibrium with gas, used as hydrate inhibitor, and it will be absorbing moisture, so it will be hygroscopic. Okay. So, for natural gas transmission inline hydrate protection, you use ethylene glycol, so that no hydrate will be formed. Okay, it will be reducing hydrate formation temperature, so that the liquid or the gas and liquid mixture, it will not reach to the hydrate formation temperature. Okay. So, another ethylene glycol, diethylene glycol, triethylene glycol. So, several types tetraethylene glycol. So, several types of glycols are there you can use. Okay. They have their own positive negative aspect, you can read there. Okay. For example, decomposition temperature or reboiler temperature will be 315 to 340 degree Fahrenheit. Water boiling temperature actually 212 degree Fahrenheit in normal temperature pressure, but you see glycol temperature, boiling temperature is more actually. So, if you maintain the temperature, water boiling temperature, then glycol will not get evaporated, or the water will get evaporated, it will create a steam and you can separate, but glycol will be staying there. Okay. So, that glycol is pumped to your contactor column again. Okay. So, diethylene glycol or tetraethylene glycol reduce vaporization because of their lower vapor pressure. Hydrate inhibitors injected in gas flow lines or gas gathering networks installed of a high pressure free water knockout at the wellhead. Removing free water from the gas stream ahead of the injection point causes significant savings in the amount of inhibitor is used. So, glycols you have seen. So, what is the chemistry of that? So, methanol. So, methanol also uses a inhibitor. Okay. So, methanol formula is like CH3OH. It can be written as C4 bonds HHHOH. Okay. Alcohol bond. The simplest aliphatic alcohol, okay, and ethylene glycol, ethylene glycol. Okay. So, ethylene glycol can be written as OH. So, here this straight lines, this end and this end shows carbon. Okay. So, this one like we do like this, then this means carbon, this means carbon, this means carbon, and we are not showing how many bonds and things are there, just we represent this straight lines as a like carbon bonded with carbon. Okay. So, whenever you are drawing ethylene glycol, you can draw like this, or you can write C 4 OH. Okay. Ethylene, so two carbons are there, and OH, H. Okay. And if I say propylene glycol, propylene glycol. So, the formula will be like this: OH, carbon here, no, propylene glycol, it will be like 3 carbon 1, 2, 3. Why 4? Yeah, 1, 2, 3. Yeah, 3 carbon. So it can be written like this: C, 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 and I have one OH here, one OH here, and remaining bonds you can make H, 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 H. Okay, and diethylene glycol, diethylene glycol, it will be like this: HO, O, again OH. Okay, ethylene glycol. So HO, CH2, CH2, O, CH2, CH2, OH. Okay, this is called diethylene glycol. So O is having 2 bond, so it will not having any other hydrogen or anything. Okay, carbon is having 4 bonds, so you have to calculate 4 hydrogen or 4 some other atom is connected there or not. Okay, so triethylene glycol, triethylene glycol. Okay, so HO, O, then O, OH. Okay, so you should try to remember how to draw this methanol, ethylene glycol, propylene glycol, diethylene glycol, triethylene glycol. Inhibitor requirement, Hammers-Mitt equation. To lower the hydrate formation temperature, amount of chemical inhibitor required. So this is temperature difference. How much depression is required? Depression of hydrate, del T. K is constant, W is weight percent of inhibitor of water treatment, M molecular weight of the inhibitor. So you can see the values are given for methane, M value given, K value given, ethylene glycol, polypropylene glycol, propylene glycol, diethylene glycol. So these values are given. So you can use these values, or in a problem sometime I give data directly so that I will not give table. Okay. Okay, see the problem. A gas will produce 10 mmSCF gas along with 2000 pound of water and 700 barrel per day of condensate, density 300 pound per barrel, hydrate formation T 75 degree Fahrenheit at the following pressure, average flow line temperature 65 degree Fahrenheit. The methanol solubility in condensate is 0.5% by weight. The ratio of the methanol vapor mmSCF 0.95. Determine the amount of methanol needed to inhibit hydrate formation in the flow line. Okay. So basic formula you have to remember, del Tm, del T equals del T equals Kw divided by 100 minus W, M is here. Okay. So if I solve it for W equals coming 100 del Tm by K plus del Tm. Okay. This is the formula. Okay. Now to prevent hydrate formation in the flow line, we need to lower the hydrate formation temperature to 65 degree Fahrenheit. Okay. So our case del T is coming 75 line hydrate formation temperature, but line temperature 65. Okay, so we have to lower 10 degree Fahrenheit. Okay, how to lower? Then we have to add certain chemical so that it will be the hydrate formation temperature will be going down and there will be no hydrate formation, although water will be there. Okay, so now use the equation del T W equals 100 del Tm 10 M value from table you can get or I can give. Okay, so here M value is given, I think. Okay, M value for DEA, this one mmSCF, gas density, water, condensate, hydrate formation, determine amount of methanol. So for methanol M value, you see methanol M value 32.04 and 2335 for K. 32.04 divided by K3225 2335 not 3 2335 plus del T 10 into M 32.04. So, this value is coming 12.07%. Now, required methanol CH3OH, required methanol in water equals 12.04% into 2000. You see this flow rate, pounds water, 2000 pounds water you have given, okay, 2000 divided by 100 because 12.04 is there. So, it is coming 241.41 pound per day. Now, methanol in vapor, CH3OH in vapor equals 0.95, it is given there, you can see the ratio of methanol vapor MMSCF 0.95, okay. So, 0.95 into 12.07, it is coming 114.47 LB MMSCF, LB plus divided by MMSCF, okay, equals coming 1.47 into 10 LB per day, okay, because 10 mmSCF flow rate, okay. So, it is coming 114.7 LB per day. Now, methanol dissolved in condensate, CH4 dissolved in condensate. So, it is coming 0.005 into 300. 300 condensate volume is given, you can see 300 and 0.5% by weight, okay. So, it is coming no, yeah, 700 barrel per barrel volume also given, 700 BPD, 700 barrel also given. So, it is coming around 1050 LB per day, okay. Now, total methanol, total CH3OH methanol, total amount of methanol is coming like 241.41 plus 114.7 plus 1050 equals 1406 LB per day. So, methanol dissolved in condensate, dissolved in condensate equals 1050 divided by 1406 into 100 equals 75%. Okay. This amount of does not contribute to the treatment. So, such treatment is not good for economic reason. So, condensate initially must be separated, after that only you should use. Thank you very much for today's lecture. Next day we will start new topic. Thank you.